have to build a radio, you'll also need to construct a radio tower that's 2 meters tall and strong enough to support a 2-kilogram satellite dish.
Once your radio is built, you'll then use that to tune into STEM FM.
Good morning, everyone. I'm so excited to prepare you for the challenges ahead. They're going to be really difficult, but we're going to give you the underlying principles that will really help you understand not just how to succeed in these challenges, but what's actually going on underneath things. So, the underlying principle for today's challenge is radio waves. Radio waves are a kind of electromagnetic radiation, and you probably heard about that idea before, but I really want to dive deep into how these concepts work. So let's think about this and compare all the different kinds of electromagnetic radiation that we have. You probably know some of them, right? So I'm going to use this kind of as a plot to think about. Up here, higher energy, higher frequency radiation. So I'll just sort of label that for us so we know where we're going. And if there's a higher frequency and higher energy, that means there's more power going in and more power coming out, depending on what's actually standing in front of all of this radiation, right? And right here in the middle of what we call the electromagnetic spectrum is a tiny little sliver in here, which is what our eyes can actually see. So does anyone know what we call that little part of the spectrum?
Visible.
Yeah, fantastic. So all of these visible wavelengths hidden in here, this is what our eyes are geared to experience, right? So there's all this electromagnetic radiation, but this is part that you can see. Now, you probably know the colors of a rainbow, right? Do you know them? Do you know the order? Do you have the acronym in your head? Come on, let's do it together. It's red, orange, yellow, green, blue, indigo, violet. You're like, Roy G. Biv, it's in there somewhere. Okay, so well done, you nailed it. If we have a think about visible spectrum. So we've got our Roy G. Biv here inside, tucked inside the visible spectrum. But what I want us to do is think about, well, what's going on in the rest of here? Because today's challenge is not about the visible wavelength, it's about somewhere else that we use to communicate. So let's first go up, right? Remember we said that there's violet up the top here, right? So we have a word that just means what happens when you go above violet. Do you know what that word is?
Ultraviolet.
Ultraviolet, right? So we've got UV in here. And then when we say, okay, remember we're going higher energy, higher frequency and so on, right? After ultraviolet, which we know if we're in the sun and we get all this UV on us, right, we can get burnt, etc. But after that, we've got particular parts of radiation that will go right through your body except for your bones. Your bones will stop them. What's that next part called?
X-rays.
X-rays, very good. And fun fact, when X-rays were first discovered, people were kind of like, what are these rays? They're kind of strange and unknown. What do we call them? Extra unknown, right? There's one last part that goes up above here, the highest kind of radiation that we know about. Just like this can burn you, this could cause you some serious problems if you're exposed to a lot. Apparently, this will turn you into an enormous green raging monster, right? Does anyone know what's the last one?
Gamma rays.
Gamma rays, fantastic. So gamma rays are very high energy and very dangerous, like properly dangerous, right? They can mess around with your DNA if you're exposed to too much. Usually comes from radioactive decay or even like a nuclear explosion or things like that, okay? So these are higher energy. So we know these are pretty dangerous. Thankfully, we are not going to be working with any of those today. We're actually going to go sort of down below. Okay, now we said ultraviolet is above. Red's at the bottom of the spectrum. So what's our word for underneath red?
Infrared.
Infrared, fantastic. And that's literally what infra means. Now, all of us are actually giving off electromagnetic radiation, and the main kind that we give off is infrared, because we're all warm-blooded. Presumably none of you glow in the dark, not giving off visible light, okay? But you are giving off IR. And obviously if you have the right camera, night vision goggles, that's exactly what we would see even if it was pitch black, okay? Now, let's keep going down, right? Underneath IR, this is kind of thermal, it's heat, right? We've got something that doesn't feel warm, but it can make things warm. You've probably got one of these in your house. Does anyone know what's next?
Microwaves.
Very good. Microwaves are down here. And the whole idea of how microwaves work is they can also penetrate through materials, but as they go through, if there's water molecules inside you, or food, or things like that, then they're actually going to get excited, they'll vibrate, and that's how we heat our food. Well, that's one of the ways, right? Now, like I said right at the top, the real kind of electromagnetic radiation we're most interested in is the final one down here, right? After radio waves, it's got the lowest frequencies, right? And so it's the lowest energy, we call them?
Radio waves.
Radio waves, right? And there's many kinds of radio waves. The kind that we're interested in, you might have noticed, as you walked in, you walked past something that's right at the top of that radio wave spectrum. What kind of radio do you think it was? Because there's at least two kinds, right? And they come with acronyms. Anyone know?
AM and FM.
AM and FM, very good. So we've got FM radios, which is the kind that you're going to be building, and then AM, which we still use today, but it's a slightly older technology. And you can see why. It's lower power. You can make an AM radio very easily. Even like a teeny tiny battery will do the job. But we're going to be working in FM today, okay? Now, like we did, you sort of zoomed in here. If we zoomed right in to FM, what you get here is different kinds of frequencies that can be accessed, right? For FM, there's a range of, from the top to the bottom, 88 megahertz all the way up to 108 megahertz. I don't know if any of you guys listen to actual FM radio, but that's that range there, right? It's why all the station numbers are like, what are they? 97.3, 106.9. They're all in this range. Now, it's megahertz. Does anyone know what hertz actually means? Or what it measures?
Sound.
It can measure sound. Actually, what it measures is sort of on the board. I gave you a bit of a clue. What do you reckon, Sophia?
Maybe like waves per second.
Yeah, very good. So it's these ideas here. Waves per second, how frequently something is happening, right? Hertz was a scientist who worked in this space, so we named this idea after him, this unit. 1 hertz means there's a wave and the frequency of it is 1 per second. So for example, if we were to draw, I wonder if you guys can tell me what kind of wave is this? Do you know what this is called from maths?
Sine wave.
This is a sine wave, right? So all kinds of frequencies here, all kinds of radiation, all have this same sinusoidal wave, which by the way, let's just pause for a second. Isn't that wild? Like sine, this comes from right angle, triangle, trigonometry. Where is that here? And the answer is it's kind of woven into the universe, right? So one of these, if you got one of these per second, that would be 1 hertz. What's mega mean?
Million?
That's millions, right? So this would be, right at the bottom here, 88 million of these per second. It's quite a few. And then remember, like we're all the way down here at radio waves. Can you imagine how high the frequencies are for here? And that's why they can do so much damage, right? So when we think about this, FM and AM, the F stands for frequency. So we're measuring how frequently does that wave go. Anyone want to guess what the A in AM stands for? It's something else on this graph.
Altitude?
Altitude is very, very close.
Amplitude.
Yeah, it's the same idea. Altitude and amplitude is like how high up and down do these things go, right? So AM is measuring this, FM is measuring this, okay? Now, this is the underlying principle underneath what you're doing today, okay? You are going to be trying to build something which is going to receive from this. And I just want to show you physically how this works, okay? So let me give you a couple of different metaphors for this. We're pretty experienced with the idea of waves from music, right? And from sound, okay? So sound is not on here. This is that's audio, okay? But it's a little illustration that I want to show you. Obviously, any musical instrument can make a lot of different notes, right? So for example, if we just play, there's like a scale. So I can make any note that I like on this, but if I strike a note without holding on to a fret, say this is the E string. This is the natural resonant frequency of that string down the bottom. And you can see how it's a very thin string there. If I strike this other E string, which is up the top of the guitar, same note, but octaves down, right? And that's because being a thicker string, its frequency is lower. It can't move as fast physically, right? A thinner string, it can move faster, make a higher pitch. And this idea of natural resonant frequency, oh, I can hear that, actually works in reverse. If I could, don't worry, I'm not going to, sing that same note back to the guitar, that exact note, that string would actually vibrate in response to me. Vibration causes sound, sound causes vibration, right? And that's exactly how your FM receiver that you're going to build is going to work. It's going to vibrate for a particular kind of frequency. Now, my last illustration for this involves, again, a bit of electromagnetic radiation. Here we go. Okay. Right now, we have all of these radio waves going all around us, hundreds and thousands of them, right? And so it's like there's a mixture, a bit like this light that you can see on here is a mixture of different lights. Notice white. White is not a color on the spectrum. What is white?
All the colours.
Yeah, we've mixed them all together, okay? Now what you want to do is try and sift out all of the different colors and say, well, where's the one that I want? So in fact, what you're going to build is kind of an electronic equivalent of saying, here is a filter that is going to just take the particular frequencies that I want, and rather than just have all of this noise all together, it's going to enable you to pick up a signal that will be how you succeed in this challenge. So, the underlying principle of this challenge is all about radio waves. You can see where they fit on the electromagnetic spectrum. We've got all these different things you can see, things that affect the world around you, and we're going to build a receiver that's right here in this special range. Good luck. It's going to require teamwork and a lot of tough thinking, but I'm absolutely confident you'll be ready.
Okay, got it.
That's good. Stop. And I'm like, oh my God, I swear if you break this right now, I'm joining blue team.